So today we have to see what effect of beam transit time and frequency limitation. Okay, so we will start with this topic. So any doubt from the last class? Any doubt, anyone? Nitish, Shishir?
No, sir.
Okay. So what is this beam transit time? Okay, what is beam transit time? So as you can see, the name suggests that this is basically a transit time or the travel time of the beam. Now, from where to where is this transit time? So basically, transit time is the time taken by the beam to travel from this point to this point. Okay, from this point to this point. So you can see basically that the deflection means this d, what did we get? So where was the expression? Over here we have written. So this is basically your d. Okay. Now, can you tell me transit time? This transit time, let us assume if it is, let me denote it using your T1. T1. Okay. So time is equal to distance by velocity. Time is equal to what? Distance by velocity. So distance is LD. Velocity is what? Velocity is your V naught x. Okay, because this is the velocity in your x direction. So VOX. So this is basically the transit time. Okay, transit time. Now there are 2-3 questions asked in ESE about transit time. So they will give you directly this value of LD and they will give you VOX, or you need to calculate VOX from this equation. So I have derived VOX somewhere. Yeah. So this is VOX. Okay, you can find it from here. So they will give you all the data and they will ask you what is the transit time, and from transit time, so let me write even transit time is equal to what? I have assumed it to be T1. Okay, one thing, this sensitivity what I had written, it was correct. Okay, this was correct. Usually you might even see 0.5 mm per volt also, you might see sensitivity. Okay, so there are sensitivities ranging from 0.1 mm per volt to 1 mm per volt. Okay, so transit time, what it is? It is LD by your VOX. So this is your transit time. Now transit time, sometimes actually what happens, it imposes upper cutoff frequency, upper cutoff, sorry, upper frequency, not cutoff, upper frequency limit of the signal that this CRO can measure. Okay, we are not going into details how it is going, just a formula is there, and I am telling you this won't be asked in your gate also. This topic won't be asked in your gate because as we are not deriving it, so it will not be asked. Okay, because in gate all those things are asked which we are actually deriving. Okay, so this is specially for engineering services. So there are direct questions, formula based question. So write one point, transit time imposes limitation, transit time imposes limitation on upper frequency limit. Imposes limitation in upper frequency limit. Okay, so basically this is actually 1 by 4th into 1 by T1. Okay, or you can say 1 by 4 T1. So this is what, this is your upper frequency limit of the signal which your CRO can detect, and that is given by what? 1 by 4 LD into VOX. So this is your direct formula that you have to memorize. Okay. Any doubt? Any doubt? Anyone? Shishir, you want to say something?
No, sir.
Okay. So the next topic that we have, it is basically a time-based generator. Okay, time-based generator. Now, what is this time-based generator? See, when we had plotted this signal, you can see when we had plotted this signal, this was what? This was given to my horizontal plate. This was the signal which we were plotting on CRO, or you can say this is the signal on which we are doing analysis, or you can say this is the unknown signal. This is the unknown signal, because if a signal is known to you, why will you do analysis? Okay, so this signal is basically what? This is your unknown signal. So when you were giving this unknown signal to horizontal plate, if you remember, the only observation that we were getting was something like this. If you remember, like this first, and this was the case. Okay, this was sinusoidal representation. Are we remembering this or not? Are we remembering this or not? That without this signal, sinusoidal representation on CRO is something like this. Did we forget? Please tell me yes or no.
Sir, can you repeat it? I lost my connection in between.
I said basically this signal, if you remember, this sinusoidal signal, this was given to your horizontal plate, okay, or you can say vertical deflecting plate. So this was what? This signal, basically we were doing analysis. This signal was the signal which is unknown, because for a known signal, we don't do analysis for known signal. If I tell you that this signal, suppose if I give you a signal, 2 sine 3t. If I ask you frequency, if I ask you amplitude, what is the phase of the signal, there is no need for analysis, because you already know what is the magnitude of the signal, what is the RMS value, or what is the frequency. Okay, all these things you know. So we basically do analysis for an unknown signal. So basically whatever signal we were giving to the horizontal plate, it is one unknown signal. Okay, so when I was plotting only this unknown signal on CRO, this sinusoidal unknown signal, the signal that was displayed on your CRO screen, it was like this. It was simple line. Are we remembering this, Nitish, Shishir?
Yes, sir.
Yes, sir.
Okay, so now which signal was actually helping me to plot this unknown signal? Which signal?
The ramp signal.
The ramp signal. So this ramp signal has a particular name. Okay, so this ramp signal is doing one, means you can say it has a very important task. Can you tell me what it is doing? Just look at the signal, what it is doing basically. It is basically mapping your time. Mapping your time. You can see this particular ramp signal or sawtooth waveform is mapping the time, because whatever is the time period of this signal, same is the time period of this signal, due to which I am able to recreate this unknown signal on my CRO. Are you getting the point? Are we getting the point or not? See, basically the
Yes, sir.
task
Yes.
of this signal is to map this signal at different time instant, or else we will get a straight line, or else we will just get a straight line. So basically what it is doing, you can see this one number point is plotted on the origin, second one, it is over here at a different time instant, this third one over here, fourth one over here, fifth one over here, sixth, seventh, eighth, ninth, 10th, 11th, 12th, and here we have the 13th signal. So basically this signal, this ramp signal is doing what? It is basically mapping the time. Mapping the time. Are we getting it or not? Are we getting it or not? So this is also a voltage. This is also a function. This signal is a ramp voltage. Okay. So you can see the voltage at this point, it is lower than this one. So that is why the deflection is more. See, the fourth point has more voltage compared to the second one. So that is why you can see the deflection is more. So that is why the time axis is being mapped. Okay. But the increase in voltage, it is linear. Are you able to visualize this or not? Please tell me. Nitish, Shishir. Okay. So now basically we are going to study about time-based generators. So the generator which is generating your ramp signal, it is called as time-based generator. Why? Because we are actually generating the time base over here. Okay. So that I can plot the signal on CRO. So oscilloscopes, what happens, what I have written, oscilloscope generally used as waveform generator. अच्छा ये तो पहले से, I don't know why I have written. Okay, so this point already I have discussed. Oscilloscopes are generally used for waveform generator that varies with time. So I'm not very good at memorizing things. Okay, so why I have written, I don't know. Means I was actually copying all these things from my notes. I thought it will be okay. So I don't know why I have written this. I can't remember actually. Okay, fine. So this point I don't know. It's okay. So next point what I have written, if the waveform has to be accurately produced, then the horizontal velocity of the beam must be constant. Very good. So this point already I had explained that, see, if I want to recreate this exact signal, so the velocity, sorry, the voltage over here should be linearly constant. See why? I will tell you. If suppose this is pi by 2, this is pi by 4, this is pi by 8. Okay, the second point corresponds to pi by 8 radian. Okay, second point corresponds to pi by 8. This fifth point will correspond to, I think, 3 pi by 4, and this will be what? Pi by 4. This is your, okay, whatever it may be. You can see that all the divisions are equal spacings of pi by 4. Can you see this or not? Can you see this or not? Once again, I will draw this. Or it's okay. So you can see I have basically divided this signal into multiples of pi by 4. That means each signal is basically occurring at pi by 4 seconds. Okay, pi by 4 seconds it's happening. You can see if this is xt, if this is t, so I am taking equal spacings. Now my this time, whichever base I am taking, this should also vary linearly. Now what is this second point meaning? See, I am going to take just 2 points over here. See, if this corresponds to pi by 4 and this corresponds to pi by 2, see, if this point is 0, this corresponds to, this is also x of t is in voltage. Okay, here I am assuming this is y, sorry, let this be z of t. Okay, so this is also corresponding to voltage only. So if this point, if I want to plot this signal on my CRO, see, look over here, this is 0 0, so obviously this is going to be plotted over here. Now see, if suppose the voltage over here is 1 volt and that over here is 2 volt, okay, so now you can see what, that from 0 to pi by 4 means there will be million numbers of points that I can take over here, but I am not taking. So you can see that I have taken equal spacings of pi by 4. So if you can see over here that this pi by 4, it corresponds to 1. If over here this voltage also corresponds to 1 or any linear rise, so this point will come over here. Okay, next you can see this is 2. Now if this is a linear function, if this is a linear function for pi by 4, if there is a rise in 1 voltage, obviously for the next pi by 4 this should be 2. Now it is not necessary that this requires to be 1 only, it can be 2 also. If this is 2, that means slope is what? Slope is what? Slope is 2 pi by 4, or that is 8 by pi. This is my slope. So for the next pi by 2, for the next pi, means sorry, for the next pi by 4, it will be what? 8 pi into pi by 2. So pi cancel, this is 4. And you can obviously see for the next, means for the next multiple of pi by 4, obviously this rise should be 4. Similarly for this one, it should be what? It should be 6. And even if you can't see, so slope is 8 by pi, and this is what? This is your 3 pi by 4. So put it over here. So pi cancel, this is 2, you can see 6. So that is why you can see there is always, because the time, it is a linear function. Okay, time is a linear function, means what? See, this is 0. After this much instant, it is 1 second. Obviously 2 second will have equal spacing. This is 2 second. There will not be unequal spacings in time. Means whatever is the time duration of 5 minutes at my place, same will be 5 minutes at your place also. There will not be mismatch in time ever. So if you want to map time, basically it should be linear function, never non-linear function. Are you getting this point? Basically mapping time, it is a linear function. Why? Because time, it is equally spaced for equal durations. Is it clear? So this is what is meant by the second point. If the waveform has to be accurately produced, then the horizontal velocity of the beam must be constant. Did we get this? Any doubt? Okay. So next is what? Unknown voltage is placed on horizontal plate. Already I have told. Okay. So known voltage, or you can say the ramp signal, is placed on vertical plate. Okay, this we already know. Fine. So, okay. So from this theoretical questions might be asked. So see carefully. So ideally, the time-based signal, it should look like this. So this is given to your horizontal plate. This is given to your vertical plate. Okay. So ideally, this should be the case for mapping this signal. But can you tell me, can we reproduce this exact signal? Can we reproduce this exact signal?
Reproduce in the sense like one on vertical axis and one on
I am
horizontal.
not able to hear you, Nitish. Your voice is breaking.
Sir, I was telling that reproduce. Sorry.
Huh? What?
Sir, I was telling that reproduce. Uh,
Every time after reproduce only there is something going on. Okay, I can't hear. Some issue. Okay, I will only tell. It's okay. Chalo, मैं बता. So this is one what? This is one ideal signal, which is possible theoretically, but we can't do it practically. Practically, we can never do such thing. Why? I will tell you. So this is our piecewise practical signal. Now, why I am telling piecewise practical? Piecewise. Now, exactly even this signal is not reproduced. Okay, the signal that we get, it is something like this. So something like this we get. Okay, I will even draw it. Don't worry. Let me draw this. Okay, so we get something like this. I want to just piecewise linearize it, so I can draw it like this. I will just draw it like this. Piecewise means what? That I am assuming it to be a function of a straight line. Okay, straight line I am assuming, that's it. So we don't need to study this one, but why this is coming, I will even explain. So now there are two things that we need to know. Okay, two things. So this much time from here to here, it is known as your sweep time, and from this time, this is known as your retrace time. Okay, sweep time and retrace time. So which time do you think should be greater than the other time, sweep time or retrace time? Which one?
Sweep time.
Very good. So sweep time should be greater than retrace time, and one more condition: for the signal to be perfectly generated on CRO, retrace time should be equal to what? It should be approximately very small, because if here it is decreasing, what will happen? This much part, it might get distorted. Okay, it might get distorted. So that is why what we are doing, we are basically, okay, can anyone tell me how can we produce this signal? How can we produce this signal? Very good. Very good. So, Nitish, have you read this RC circuit? Good. So, we can produce this signal using RC circuit. Okay. RC circuit. Can you draw the circuit diagram? Can you draw? Okay. चलो कोई बात नहीं. I will only draw. So, we can make this common base. So what can we take? Plus VCC or plus 5 volt? Okay, let me keep it as plus VCC only. This is R, this is C, this is V naught. So this is what? This is basically what? I also know this is one BJT. So what is this? Which mode is it operating? Can you tell me that? Which mode? Common emitter. Very good. Common emitter. So you can see basically that this sweep time, okay, this sweep time, tell me, will it be a fixed or will it be different, variable? Will it be fixed or will it be variable? See, this BJT, it is either working in your cutoff region or saturation. So while it is in saturation, what will happen? Your capacitor will discharge. Why? Because when it is in saturation, we know there is a we know that there is a low resistance path between your collector and emitter at saturation. So this capacitor, it will discharge. Even you can put one resistance over here. Okay, you can put one resistance, but that resistance will be very small. Ideally, what you want? Ideally, you want your retrace time to be very, very less. Okay, so that is why you can see capacitor will discharge instantly in this path. Why? Because there is no resistance, but practically there will be some emitter resistance inbuilt. So that is why there will be some retrace time. Are you getting the point? So this BJT, it will work either in your cutoff mode or in saturation mode. In saturation mode, it will discharge. Okay, so you will get this retrace time, and when it is your in cutoff mode, so in cutoff mode there will be no means low resistance path, so this capacitor is going to charge in this path, and in cutoff we will get this sweep time. Tell me, is this clear? Is this clear? So this might be asked. Okay, this might be asked. Now I asked you one question. See, different signals will have different time period. So do you think keeping this sweep time constant, is it a viable option? No, it is not viable option. So for manipulating or varying the sweep time, what I can do, either I can vary R, or I can vary C, or I can vary both. Okay, I can vary both. See, when this BJT, it is in your cutoff mode. Okay, in your cutoff mode. So this V naught will be equal to what? V naught will be equal to VCC 1 minus e to the power minus t by RC. Now I am not explaining from where we are getting this. At least this much we know. This much we all know. Okay, so you cannot say, sir, from where did you get this? Array, I have just used the transient equation. Okay, transient equation. So from that only I have got this. See, if this VCC was present till infinite time, capacitor will charge till Vc infinite is equal to what? It will be Vcc. Okay, initially the charge on capacitor, it will be zero, because during retrace time you can see the capacitor is fully discharging. Okay, fully discharging. So that is why Vc0 is equal to 0, and this is RC circuit, tau will be equal to RC. If you put it in the equation of transient, you will get this. Okay, so I am not doing anything. So what did I say? That the sweep time, it needs to be variable. So either I can vary R, or I can vary C, or I can vary both. So which is the most viable option? Vary R, vary C, or vary both? Yes, very good. So you vary R. So that is why in your CRO you will be seeing that there is one knob. Okay, there is one knob where basically you manipulate the sweep time. Okay, you manipulate the sweep time to get the signal. If you have seen, means you take the signal from this origin to this point. Okay, so you basically do what? You manipulate the sweep time so that easily you can do analysis on this signal. So basically you are doing nothing, you are manipulating this resistance in your sweep time so that you can adjust this time base. What about retrace time? Do you want it to be variable or fixed? Retrace time, do you want it to be variable or do you want it to be fixed? What do you want? Fixed. Obviously you want it to be fixed, and you want it to be as low as possible. As low as possible. So you can see there is no resistance. Ideally there is no resistance in the emitter path, so retrace time should be 0. But practically, there is a very small amount, not a very small, it is a means somewhere around 100 ohm. Okay, by default there is a resistance in your emitter terminal which is as high as 100 ohm. So there is a negligible amount of retrace time also. Okay, why? Because this capacitor, it is either in your millifarad region or microfarad region. So the time you can see, it will be also in your milli or microseconds. Okay, so that is why there is a negligible amount of retrace time. Is it clear? Is it clear? Any doubt in this? Okay, so up till now, what we have studied? We have studied your CRT. Okay, we haven't studied what is cathode ray tube yet. We have studied your CRT. Okay, everything we have studied about CRT. Now, with the help of this CRT only, we are going to see basically what is your CRO. Okay, CRO. So this is now your cathode ray oscilloscope. So this is the complete apparatus of CRO. Okay. Now in this CRO, you can see I have taken few things over here: vertical amplifier, delay line, time based generator. Even the arrow is different over here. Okay, arrow is different. So let me tell you that this is basically what? This is the CRT that we have studied. This is the CRT. Now this signal, okay, this is your what? Can anyone tell me? Okay, I should have taken it something else. Now this signal is basically, can anyone tell me what is this signal? Look,
Unknown,
where is this huh? What?
unknown signal that we have to measure.
Yes, very good. So look over here. Basically, this signal we are giving it to your what? We are giving it to your horizontal plates. So that means this is our unknown signal. So this is my unknown signal. Okay. Now, have you seen one CRO? CRO. So basically, CRO, there are probes and cable. Okay. Let me show you what is probe. Then you will be able to understand what is probe. See, basically this is your probe. Okay, this is all, this is cable, this is probes. Okay, this is also probe. So these are basically the probes of CRO. Now this has some resistance and capacitance which we are going to deal later on. Probe capacitance, probe resistance, all those things we are going to see. But have you seen this probe cable? Either it will look like this or like this. Have we seen this?
Yes, sir.
Okay, so this is your probe cable. Okay, this is what? This is probe and cable. Now this is what? This is your vertical amplifier. Now why do we require amplifier? Can anyone tell me? Can anyone tell me why do we require amplifier? Vertical amplifier especially.
To enhance the amplitude of the signal.
See, basically, yes, correct. You are correct. The unknown signal that we have, okay, unknown signal. So sometimes what happens if I am measuring a voltage. Now this might be either in millivolt region, okay, millivolt region. So do you think if this vertical amplifier is not present, okay, if this vertical amplifier is not present, is this millivolt value of signal, is it capable to bend this electron? Because whatever is the voltage of this signal, proportional to that, the signal means, sorry, the electron will bend, and which will hit your screen, and you will see the fluorescence displayed on the screen. Okay, so do you think this millivolt of voltage, will it be able to deflect the electron beam of this plate? Do you think so? No, it won't be able to do that. So basically, we require what? We require a amplifier, and that amplifier is basically what? It is your vertical amplifier. Okay, vertical amplifier. Then tell me one thing. This is actually your time base. Okay, so up to this point, hold. Next thing I will be explaining. Now let me ask you, see, basically this is the time base. Now why I have connected it with the unknown signal? Because I need to know. So there are different apparatus over here. You have seen, just now we have seen, there is time based generator. Okay, so time based generator will basically generate this signal. So it will generate signal based on the time period of this signal only. So that is why it is connected over here. So now tell me, why is this time base not connected to some horizontal amplifier? Huh? Some horizontal. Tell me. Now, why I am telling horizontal amplifier? Because this is being given to the vertical plates, and vertical plates deflect signal in your x-axis. If you remember, this is x-axis, this is y-axis. So vertical plates deflect signal in your x-axis. That is why horizontal amplifier I am telling. So why is there no horizontal amplifier? What happened? So we can't think or what? अरे
Sir,
obviously. हाँ बोलो बोलो नीतीश टेल.
time period won't need any amplification. Like
Yaar, your
we can,
voice is not at all clear. I can't hear you. Shishir, are you able to hear him? So Shishir is not
No,
able
sir.
to hear me. So there is some problem, Nitish. Nitish, are you able to hear me? So that is one important thing. So then it's okay. I will explain. I will explain why. So this time base is generated, okay, generated in the CRO itself. Okay, CRO itself. So you don't require basically unknown signal. It can have less voltage, means the amplitude can vary or sinusoidal or any unknown signal. It can be low, it can be even high. But the time based generator, it is basically a known signal. So a known signal, obviously I can keep this voltage high. I can keep this voltage high. It is up to the machine, okay, or the manufacturer who is manufacturing basically, he or she, they can actually keep this value of voltage high. So there is no need for amplification in the time based generator. Okay, so time based generator. Now you can see there are two switches over here, A and B. Okay, A and B. Now this CRO, this complete setup can work in two mode. So whatever we have seen up till now, like this one over here, this was displayed like this. This is actually working in your YT mode. Now, what is this YT mode? YT mode is the mode of CRO in which we are giving the known signal as a ramp signal. Okay, there are two modes of CRO. YT mode, the switch is in A position. Okay, and here the signal given to your vertical plate is ramp. Okay, ramp. That means what? Basically, we are plotting one unknown signal with respect to time. With respect to time, we are plotting one unknown signal. Now, there is one more mode where we have XY mode. Now, in XY mode, basically, we keep the switch in your B position. So here also the signal is given to vertical plate only. Okay, vertical plate, but this signal is a known signal, is a known signal. Now this can be either sinusoidal, okay, it can be sinusoidal, it can be a ramp signal. Okay, usually we take it as sinusoidal signal. Why? I will even explain that. Okay, why we take sinusoidal signal, that also I am going to explain. Usually we take it as a sinusoidal signal, which is a known signal. Known signal means already I know the time period of the signal. If I know time period, that means I know the frequency of the signal, and I know even the amplitude of the signal. Okay, so this is a known signal where this is actually, it can be a sinusoidal signal, it can be even a square signal, or it can be a triangular signal, but usually we take sinusoidal signals only. Why? I will explain later. Okay, so basically in YT mode we do analysis for unknown signal. Okay, unknown signal. in your XY mode, basically we determine what? We determine the frequency phase of the unknown signal. So, right? Frequency and phase of the unknown signal we try to find out in our XY mode. Is it clear? Is it clear? Now,
Yes,
what
sir.
is this? This is PDA. Okay, I have shown it over here. PDA, post deflecting accelerator. Now this is also one kind of accelerator which helps the electron to strike the screen at a greater velocity so that the luminescence is more. And here we have aquadag. Aquadag is basically a coating which we are going to write at the moment. Okay, so there are few points that I want to dictate. See, already I have discussed YT mode. Okay, how to display this signal in YT mode already I have discussed. So, okay, fine. The attenuation factor of CRO, this also we have to see. Okay, so I want to dictate few points to you over here. Okay, so just give me a minute. Let me open my notes because I also don't remember. So point wise, I have to write it. Okay, so everyone note down. So this will help you in your this thing. What if there is a multiple select type question? So if some theory questions is asked, you should be knowing. Okay. So most of the things, if you have noted, you will see that we have actually done those. Means we have written somewhere or the other. Okay, I have discussed. So PDA, I told you it is post deflection accelerator. So right first point. First point is CRO is electronic peak voltmeter. CRO is electronic peak voltmeter which senses both AC and DC signal. Okay, which senses both AC and DC signal. CRO is peak electronic, sorry, CRO is electronic peak voltmeter which senses both AC and DC signal. Second point, CRO works on principle of thermoionic emission. Already I have told this thing. CRO works on principle of thermoionic emission. Okay, CRO works on the principle of thermoionic emission. Probe and cable, next point, probe and cable are used as connecting media. Probe and cable are used as connecting media to connect unknown signal to vertical amplifier. Probe and cable are used as connecting media to connect unknown signal to vertical amplifier. Okay, I didn't explain about delay time. Delay line. Just give me a second. So, what is this delay line doing? So, just see. First, understand over here. Then we are going to write the next point. See, this vertical amplifier. This is basically an amplifier circuit. Even this probe and cable. So, let me show you the diagram, the circuit representation of probe and cable. So you can see this is basically the circuit representation of probe and cable, RP and CP. There are one resistance and capacitance in parallel. Okay. So usually what happens, we are giving unknown signal over here, we are amplifying it. So what happens, tell me, if this is the signal, do you think will there be any phase difference? I am asking phase difference between this signal and the same signal which is amplified. Will there be any phase difference? Phase difference means you can say over here will, okay, let me ask you in a simple language, will there be any delay in the signal between here and here? Delay. Will there be delay in signal? Because there are different components working in your amplifier. So obviously there is going to be some delay, and that delay it is not going to be negligible. Okay, it is not going to be negligible. Okay, so what happens, basically there is some delay, and the time based generator, I have produced this signal based on the time period of this unknown signal. Okay, and if there is some delay, okay, which is not negligible, if I am giving this signal over here, so that means there is some phase difference between the time based signal and this amplified signal. Are you getting the point? Are you getting the point? So basically this delay line, it does what? It synchronizes once again this signal with respect to the time based signal. So there is negligible amount of phase difference between your amplified signal and your time based signal. Is it clear? So that is the purpose of your delay line. Any doubt? Any doubt, anyone? Okay. So once again start noting. Okay. So third point I told. Okay, fourth point. Fourth point. Most of the properties of CRO are decided by vertical amplifier. Most of the properties of CRO are decided by vertical amplifier. Most of the properties of CRO are decided by vertical amplifier, like input impedance. We are going to discuss this input impedance. Input impedance, bandwidth, rise time. So these 3 points only we are going to discuss. So that is why I have mentioned these 3 points only. Bas. Okay. Next point, vertical amplifier is a multi-stage. Vertical amplifier is a multi-stage MOSFET amplifiers. Vertical amplifier is a multi-stage MOSFET amplifier which provides high input impedance. Why high input impedance? So first note down, then let me know. Vertical amplifier is multi-stage MOSFET amplifier which provides high input impedance. Vertical amplifier is multi-stage MOSFET amplifier which provides high input impedance. So now tell me, why high input impedance? Fast. So Nitish, why does an amplifier require high input impedance, low output admittance? Can we tell this or not? So this is the ideal characteristics of amplifier. High input impedance, low output admittance. Sorry, low output impedance. I am admittance, I am telling. Sorry. ऐसे कर रहे हो तुम लोग, है ना, मतलब. So did we forget even loading effect? You guys are studying. Nitish, haven't I told this in the class? So then, please don't forget basics thing, okay? If you forget basic thing, na, then it will be really very difficult in the end. Okay? So next point. Next point. Due to high input impedance, loading effect is minimum. Due to high input impedance, loading effect is minimum. Okay. Next point, horizontal plate deflects electron. Horizontal plate deflects electron. Horizontal plate deflects electron in top or bottom. in top or bottom, in bracket write y coordinate. Next point, vertical plate deflects electron. Vertical plate deflects electron in horizontal direction, or first you write in left right direction. Vertical plate deflects electron in left right direction, in bracket right horizontal direction or y coordinate. Okay, y coordinate. Next point, combination of horizontal and vertical plate. Combination of horizontal and vertical plate. Combination of horizontal and vertical plate act as position controller. Combination of horizontal and vertical plate act as position controller. Combination of horizontal and vertical plate act as position controller for electron. Bracket xy coordinate. Okay. Next point. Delay line is inserted between. Delay line is inserted between. Delay line is inserted between vertical amplifier and horizontal plate. So once there was a question, if you see, I think GATE 2003, where is delay line introduced? There were 4 options. One of the option was between vertical amplifier and horizontal plate. Another option was between vertical amplifier and vertical plate. Another option, there were few more options were given. So the correct option is delay line is introduced between, delay line is inserted between vertical amplifier and horizontal plate. So write your point. Delay line is inserted between vertical amplifier and horizontal plate to maintain synchronization between horizontal and vertical plate. To maintain synchronization between horizontal and vertical plate. Next point. Combination of 4 plates. Combination of 4 plates deflect electron into their desired position. Combination of 4 plates deflect electron into their desired position, which is proportional to unknown signal. Which is proportional to unknown signal. Next point. A thick phosphorus coating. So now where is this phosphorus coating? Just a second. So this is your okay. So what I said, a thick phosphorus coating act as a screen. A thick phosphorus coating acts as a screen which has fluorescence property. A thick phosphorus coating acts as a screen which has fluorescence property. Okay. Next point, PDA. Force deflection accelerator. So PDA provides linear motion. PDA provides linear motion to deflected electron. PDA provides linear motion to deflected electron so that electron hits the screen with high velocity. So that electron hits the screen with high velocity. Okay. Next point, aquadag. Aquadag. Now what is this aquadag? Aquadag I shown you over here. Okay, so this is aquadag. Aquadag is used to attract aquadag is used to attract electrons aquadag is used to attract electron which do not have sufficient amount of energy. Aquadag is used to attract electron which do not have sufficient amount of energy. Okay. So next point. Next point. Equivalent input circuit of CRO. So this we haven't discussed, but we are writing. How many more points do I have? So few more points. Equivalent input circuit of CRO. Equivalent input circuit of CRO is parallel RC circuit. Equivalent input circuit of CRO is a parallel RC circuit due to connection of probe cable and amplifier. Okay. Equivalent input circuit of CRO is parallel RC circuit due to connection of probe cable and amplifier. Next point, delay line is only used in YT mode of operation. Delay line is only used in YT mode of operation. Delay line is only used in YT mode of operation. Next point, delay line is not used in XY mode of operation. Delay line is not used in your XY mode of operation. Okay. Can you tell me why? Okay. So when we study XY mode of operation, at that time I am going to ask you this question once again. Why don't we use delay line? Okay. Why we don't require delay line, that I am going to tell you. Okay. So next point, time period and frequency of time period and frequency of time based generator. Time period and frequency of time based generator is variable. Okay, is variable. So quality mode, just give me a minute. All these points do we need to write? Yes, so we need to write this, right? So CRO is image plotter. I think I have shared this in the first slide. So this is image plotter, I have already said. No need to write that. YT plot is amplitude versus time. YT mode is used for, this you have to write. Next point, right? YT mode, YT mode, YT mode is used for measurement of peak RMS. YT mode is used for measurement of peak value. Sorry, peak value should be written. Peak value. YT mode is used for measurement of peak value, RMS value, peak value, RMS value, average value, peak value, RMS value, average value, time period, and frequency. YT mode is used for measurement of peak value, RMS value, average value, time period, and frequency. Okay. In place of it is XY plotting X. Okay, so write one more point. XY plotting, XY plotting, XY plotting is also known as Lisa-Just pattern. XY plotting is also known as Lisa-Just pattern. Spelling for Lisa-Just pattern, let me write. Okay, so this is your Lisa-Just pattern. So this is only one time where I dictate few points, okay? Or in none of the cases I dictate anything. So this is one place only. So that is why you might have seen that I am not very good. Okay. Chalo. So any doubt up to this point, tell me. Any doubt? Okay, fine. So now let us study about the most important thing that is your screen. Okay, screen of CRO. So first, let us see in your Google. You might have seen that the screen of CRO, there is it looks kind of like a graph paper. Okay, have you seen it? Yeah. So it looks something like this. It looks like graph paper. What? No, you haven't seen the screen of CRO. It
No,
looks
sir,
like
it
this.
was
Okay.
for previous question.
Okay. Okay. Exactly. This one you can see. So it looks kind of like your graph paper. Okay. So it is something like this, and means origin you can take it to be here also. It is up to you where you want to fix the origin of the signal, because you can manipulate the signal. You can take origin over here. Okay, if you want, you can take origin over here. Wherever you want to take, you can take basically the origin of the signal. Now for my case, I am deciding that the origin is over here. Okay, now there are basically, see, when you are working in your YT mode, at that time I am telling, so this is your y axis, this is your x axis. Okay, so now the x axis is basically what it is in time, and y axis it is in your volts. Okay, it is in your volt. Now there are even small divisions over here. 1 2 means, sorry, 1 2 3 4 5 6 7 8 9 10. Okay, so there are in total 10 divisions over here, and even 10 divisions over here. 1 2 3 4 5 6 7 8 9 10. So there are small divisions. Okay, if you look at the screen, don't know. You can see, look over here, there are small divisions at this point. Okay, so everywhere there are small divisions. So this is actually, they have also kept, this is the origin, but it's not required. You can even take it over here if you want. You can take it over here, but you can see especially that they have given reading for this dual trace oscilloscope. So you can see there are, means the origin has been decided in the middle of the screen. You can manipulate the signal to bring it over here. Okay, either you can manipulate the signal to bring it, means the origin over here, or you can even do what, if you want, you can zoom this screen. Okay, you can zoom the signal. You can just keep one of the upper part of the sinusoidal, okay, the positive half frequency, positive half cycle, you can magnify it over here. So there are different ways. Okay, there are different ways in which you can do. So there are, these are the two channels, this is channel 1, this is channel 2. Okay, so this you can see, this is XY mode, this is chopping. Okay, chopping, what is chopping? So chopping is not required. Okay, chopping is not required, but still I am going to show what is chopping. And over here we have, this is line, here this is AC/DC. So this is if you want single signals. Okay, if you don't want dual, so channel 1, channel 2. So I don't know what is this external trigger, I don't know what is this. So this is for selecting the time base. Time base means this one, this base. Whether you want it in your millisecond, see there are different scales. Whether you want it in second, whether you want it in millisecond, whether you want the time base to be in microsecond. So different time bases are also there. So this is one good thing. Okay, it's very good that I got this diagram. So anything else that we need to explain? See, what is this? What is this knob used for? What is this knob used for? So at the moment, you just see this knob is used for level setting. So we are going to see what is level setting. And if you are able to see, there are two arrows also. So these two are the same. So basically there are two arrows. So basically what you can do, so this option is not available. Is it getting downloaded? I don't know. Okay. What happened? So basically what happens, you can either take this signal above or below. Okay, so this signal can go down also, above also. So basically it does the level setting of the signal. Any doubt up to this point? Tell me. Any doubt, anyone?
No,
Something
sir.
which we haven't understood? Okay, so this diagram is very good. I will keep it over here. So it got downloaded over here. So even I didn't know this feature was present. So that directly I could download. Wow, this is very good. I will work upon this now. Let it be. I never knew this feature. Okay, from last 2-3 years I am using this software. अब कहाँ download हुआ? So this is where it is getting downloaded. I never knew this feature was present, that you could directly download one image on this ongoing presentation. Okay, I never knew. So I was telling that there are different means divisions present over here. So even for voltage also you can measure it to be in volt, millivolt, whichever way you want. Time also you can divide. Okay, time also you can divide over here. So basically the sensitivity, see, if suppose you have a signal that looks something like this. Okay, this is one sinusoidal signal. Now if I ask you, if suppose I give you that the vertical sensitivity is let me give you 2 volt per mm. Sorry, here I haven't defined per. So what I can divide, so basically I didn't tell you what is this SY. So SY, vertical sensitivity. What is vertical sensitivity? So vertical sensitivity is basically the voltage per division, okay, per division of the scale. So it is basically in volt per division, or it will be millivolt per division, so that you can directly see from the unit of the sensitivity. Okay, so it will be either volt per division, millivolt, microvolt, whatever it can be. So you need to see it. So this is basically what sensitivity in your y-axis. Now it can be either, I told, volt per mm, okay, volt per mm, or it can be even volt per centimeter also, volt per centimeter, whichever way you want to take. See, this is 1 mm, this small division, and this one block, it is 1 centimeter. Okay, why to come over here? Already I have downloaded this. So this much is what? This much is 1 centimeter, and the small spacings, these are, means that there are 10 divisions, so this is 1 mm. Okay, 1 mm each. So either you could have in volt per centimeter, volt per mm. Okay, so next we have is what? Time base. Now time base, you can manipulate it yourself. Here it is given. If you want this, what is happening here? So if you want this to act as your 1 second, means a multiple of 1 second, so you can keep it over here. If you want this to be a multiple of 2 second, place your knob over here. If you want it in microsecond, you can see there are different settings ranging from 1 microsecond to 50. Then you have in, sorry, in millisecond, this was milli, and this was even in your microsecond. You can see there are different from 0, 20, 10, 5 to 1.5 microsecond ranges also you have. Okay, so basically your Sx is what? It is your horizontal sensitivity. Now horizontal sensitivity, it can be what? It can be second per centimeter, or it can be millisecond per centimeter, or it can be microsecond per centimeter. Similarly, you can even define it in for your mm also. You can divide it in your mm also. Is it clear? Is it clear? Any doubt in this? Tell me. Okay, so now see over here, if for this particular case, if I give you, suppose if I give you Sy is equal to, let me give you 2 volt per centimeter, okay, 2 volt per centimeter, and Sx is equal to 1 second per centimeter. What is the peak value of this signal and what is the time period of this signal? So this I have drawn for your half wave, means the positive half cycle. The negative half cycle I haven't drawn. So can you tell me? Or we can even draw it like this, it's okay. Why not to draw? Now tell me. This is not exactly looking like sinusoidal. Okay, so peak value, see, now there are few confusing things also. Peak value is what? Peak value is this, okay, this much. So peak value is what? It is equal to sensitivity in the y direction into the number of divisions. So number of division, you can see this is 1, this is 2 centimeter. So 2 centimeter. So this is 2 volt by centimeter into 2 centimeter. So centimeter, centimeter cancels. This is 4 volt. If you want to calculate time period, so time period is Sx into number of division in x-axis. So that is 1, 2, 3, 4. So this is 4 centimeter. So this is 1 second by centimeter into 4. So this is equal to 4 second. Okay, 4 second. So now if you, who said time period is 4 second? Here Nitish, time period of this sinusoid I even told that this is what, this is the positive half cycle. That means there is a negative half cycle also. So time period is equal to, so this is half time, I should have also written. So time period is equal to twice into half time. So that is 8 second, and peak value is 4 volt. Now sometimes in the question it is asked peak to peak value. Now peak to peak value means from here to here. Okay, so peak to peak value, so that is what you have. Peak to peak value is 8 volt. So remember to see the question properly. Okay, remember to see the question properly. So as we have time period, I can even calculate the frequency. So that will be 1 by 8 or 0.125 hertz. Okay, any doubt? Any doubt? Tell me yes or no. So this is what, this is basically the screen in your YT mode of operation. Now I think we don't need to discuss, basically means I had actually made this. Now do you think we should discuss over here that basically how this signal is being plotted over here? Is it required? Is it required anymore? Because already we have seen this. Okay, so this thing, okay,